Good morning, you absolute math nerds who tune in to watch math on a Sunday morning. I hope you're doing well. I hope you've proved lots of theorems this week and this weekend. I guess, I should. How do I pop out chat now? Go away. I should probably plan more things ahead of time to talk about in case people don't have questions. Office hours on Sunday, yeah, Deepak. Nice to see ya. Nice to see ya. It's pretty much. I mean, I've got commitment issues with this channel and streaming, but it's worked out to basically be every day of the week, except Thursdays. So I don't know if it's going to continue like that, how long it will continue for, but that's what it's been like lately. Yeah. So, I was thinking as I was making my breakfast this morning, I was like, oh, man, yeah, should think for half of a second for a topic to sort of ramble about, in case there aren't a lot of questions today. And, well, one thing that came to my mind is we've been studying D modules, so it's way more definitions and theorems. Well, yeah, I mean, I guess when you get to any sufficiently advanced or intricate kind of mathematics, yeah, it's a lot of time learning definitions, and it also depends on where you're starting from, right? Like if you're not familiar with a lot of the stuff that goes into the basic definitions of D modules, well, then yeah, you're gonna spend a lot of time learning definitions. Yeah. And the theorems become harder to prove because the definitions are so intricate. How do I organize my PDFs? Not very well. Not very well. Yeah, I've got like a. So here's my. Here's sort of like the folder that's all the PDFs that are relevant to my research. As you can see, there's a bunch of things that are just dumped in here randomly. Just a whole bunch of random stuff. Some things were organized by like, spring, summer. I had my notes organized. Yeah, there's things organized by some topics, but yeah, they're not organized very well. In total, I used to be more organized. I used to be more on top of like keeping, winter 2023. I'm gonna keep my notes in there, but I've also got things like on GitHub. I've got projects on GitHub. I've got projects on Overleaf, so they're also like spread out all sorts of places. Yeah, it's kind of like the classic, cliche about the professor with a messy desk. Have you ever seen Andrew Weil's desk? Have you ever seen his office? Let's take a look. Andrew Weil's interview. Yeah, look. Look at that. I feel like that's me. Oh, good morning, Russell. I feel like this is totally me right here, but instead of the physical mess of papers, it's like sort of ethereal electronic mess of papers. It's like the mess in my mind. And oh, it's your birthday. Oh, happy birthday, Deepak. Happy birthday. Hope you're doing something fun, like solving a major theorem. Let's see. Can we pull up an image of Konstovich? Well, there's somewhat of a clip there. Yeah, I wonder if I. Yeah, I wonder. Oh, we should check out the birthday problem. I wonder how many other people in chat. You know, the birthday paradox, birthday problem. Yeah, I want to figure out. Only 23, so I don't know. If we have 23 people in chat, then there's a good chance that it's someone else's birthday as well. At a certain point, I feel like organizing by year gets difficult when the study spans over said years. Yeah, that's true. But it has been it has been useful to try and stay organized. It does help me find things that I'm looking for. And it is really annoying when I know there's some document somewhere and I can't remember like where I would have put it, but I'm like, okay, I know I did these calculations. Like that happened to me recently, and the I finally found it, but it was in a not the title of the PDF was like not very enlightening, but I did find those calculations. Yeah, it's also the interesting thing about that is also thinking about memory with aging. And I now use my like calendar more, my Google Calendar on my phone. But for a long time, I just always kept everything in my head, and it got to be a bit much. But I was pretty good with it. I would not forget things, certain things. Anyways, I was decent at it. Oh no. Sorry, I just think I spilled coffee on my plant. Or maybe it was just, I feel, it could have been the French press being too close to it and maybe hurt my plant. Oh no. Only 10 people watching, probably might not on our side. Well, maybe, but then toss me in the mix, so that makes 11. But it's not my birthday today. But it's the odds that someone shares a birthday with Deepak still aren't high. But the odds that someone shares the birthday with someone else in chat, that's maybe a bit higher. I don't know. Post your birthdays in chat. How would the birthday paradox look in an alien civilization where the days and months are longer? Well, that wouldn't be too hard to. I don't think that'd be too hard to figure out. I mean, yeah, the formula is basically right here, right? So the probability, one can compute the probabilities right here. So, we got. Yeah, you just take. It looks like you would just take the total number of days in the year. I'm not sure the months. Yeah, the months part doesn't matter. It would just be the number of days in the year because we're looking for the same. Whoa, same birthday as Sarah. Wow, that's awesome. Yeah, I don't know if he's in chat. Sarah, if you're here, say hi. I mean, as far as I know, he's still putting out papers. So, I don't know why he'd be in my office hours. Probably to give me advice. Oh, you've got the same same as Vibo. September is the most common birth month. Yeah, well, let's see. That makes it um, December. So, right, probably conceived around Christmas. That makes sense. I would have assumed Valentine's Day, post 9 months from Valentine's Day, um, which is like November, I think. Yeah. Anyways, yeah. We this is okay. This is all we can see of his office, but yeah. The interesting thing is, I bet he knows. I bet he knows where everything is in the office. In the same way, sometimes my life, either physically or digitally, turns into a certain amount of chaos, and yet I know where things are somehow sometimes. Do I have any intuition for what's special about normal subgroups, or why general subgroups can't be quotiented by? Understand technically, just looking for intuition. That's a good question, actually. Konstovich's office is seen of the Shaw Prize 2012. Oh, okay. I'll put that in after. Your intuition is that normal subgroups are quotientable subgroups. They have structure, which can be ignored. Yeah, I mean, I don't know. I don't know if I can offer a good intuition about it, because I mean, to me, it is just kind of a technical fact that it is just a technical fact that the reason, if you have a non-normal subgroup of your group, is just that the well, multiplicatively or additively, take your pick, but it's just that the group law, the sort of natural thing you would guess to try and turn this into a group is still it's not well defined. You don't get a well defined multiplication anymore when it's not normal. But in fact, taking these quotients, even when h is not normal, is still useful, actually. Not to think of it as a group, but when we're thinking of G and H as topological groups, then we might still want to consider this quotient as a topological space. So it will fail to be a group, but we'll still get a topological space, and we definitely want to consider that. Like, there's plenty of times when you might have like some integral over a group, and you might break it up into an integral over the subgroup and the cosets or something. Why don't all subgroups have structure that can be ignored? Well, I don't know. I'm not so sure. I'm not so sure it's about structure that can be ignored. But yeah. So one other perspective I would maybe take is that so notice that if n is normal, then if we take the quotient map from G onto n, then then n is the kernel. So if I call this pi, n is the kernel of pi. And conversely, if you have any group homomorphism, then the kernel is a normal subgroup. So normal subgroups are the exact same thing as specifying kernels of homomorphisms. So I don't know if this helps or if this is any more intuitive, but it's somehow, you can think of it as like it's about the way that the group relates to every other group. It somehow, I guess in a sense, can be viewed as the collective structure of the whole category of groups, right? So a subgroup is normal if and only if it appears as the kernel of some homomorphism. I guess that doesn't really say why you should be able to. Those are the only ones you should be able to quotient by. Yeah. So sorry. I don't know. I don't know if I can come up with an intuitive explanation that I would also be happy with. That's not that's still true, I guess. I really think it's just a sort of technical thing. You just write down one example and you go, oh yeah, it's not well defined. Or I mean, even in the process of trying to prove that you have that this group operation is well defined, right? You maybe just hit a place where you need the assumption of normality. So then you say, okay, well, let's assume that, and then you try to cook up counterexamples to show why it definitely fails without the normal hypothesis. Yeah. Okay, we're gonna look up Konstavich's office. Konstavich. What was it? Shaw Prize? This first one, maybe? Can I watch other videos on my stream? Probably not. I get demonetized. Actually, that's fine. Actually, my streams aren't monetized anyways. Okay, here's his... Wait, I thought that was his office for a second. Oh, it looks like we get a glimpse of it. No. Yeah, there we go. Okay, there we go. There's a glimpse. There's some stacks. Wow, those are nice drawings. That's a nice trefoil knot. Oh, here we go. Here's some more office. Yeah, that's not... Oh, okay. Yeah, okay. Nice. Hey, Edit Smith. So, one of the other things I was going to talk about is... the fact that Magic the Gathering is Turing complete. Are you late or am I early? Remember when XQC got demonetized for streaming the Olympics to hundreds of thousands of viewers? Oh, really? Huh. Okay, I should stop streaming other people's videos then. What a hero, though. What a hero. Wait, that's so weird. Can't you just... Do you have to pay to watch the Olympics? I mostly watched just, like, clips afterwards this last year. Which, by the way, this last Olympics that happened... I mean, maybe it's just because meme culture is at an all-time high, but I feel like... we've had quite a few... Olympics that a lot of memes could have come out of, but for whatever reason this year, like, there was just a lot of characters, a lot of memeable moments came out of the Olympics, and I love that for us. I do. Yeah, but I wanted to mention this paper. So Magic the Gathering. Let's see, do they have examples of cards? I mean, probably. All you guys are, everyone in this chat is a nerd, so Hate to break it to you. Sorry if this is how you find out. Um, but so I assume you've heard of this, but it's like a card game. It's like Pokemon for adults, basically. Let's see if there's images. But yeah, so you've got yeah, whatever. Okay, Pokemon for adults. You get the idea. There's creatures and whatever, and it costs a stupid amount of money for drawings on cardboard. This paper here proves that actually Magic the Gathering, and so here's why I say it's Pokemon for adults, because the rules are are much more complicated. There's a lot more going on, and there's a lot of like if then statements, and there's yeah, how else to say it? Yeah, it's just very, yeah, like anything you could possibly conceive of doing in this game, there's probably a card that allows you to do it. Like there's a sequence of cards that you can play, which basically there's a card that forces a player. It says target player loses game. It forces the player to lose the game, but there's a certain way you can set it up so that you have this card in your deck, but you force your opponent to take this card, and then they have to choose either to use it on themselves and lose the game, or to not use it on themselves, but then it's set up so that there's a chain reaction so that it just goes around through this loop and it sends them back to that same position. So either the game goes on forever or your opponent decides to use the card on themselves and lose. So it's like really you can do it. It seems, well, before this paper, it seems like you really could do anything in this game. What this paper is doing is they prove actually that Magic the Gathering is Turing complete. So it basically anything your computer can do, anything the device you're watching this on can do, can in theory be carried out using Magic the Gathering. And not only that, but at least at the time of this paper, so I guess 2019. At least at the time of this paper, the deck the deck they produce is tournament legal, because Magic's been around for many years, and cards have been banned and stuff because they were overpowered and whatnot. And the deck that these people came up with was, at least at the time of, oh my god, there's something called Kazul Warlord. Okay, that's so funny because I went to a school on spelled slightly differently, Kozul Duality. I'm gonna have to make a meme. Of this for my. I'm gonna have to make a meme of this for my research group. Amazing, incredible. Hey, you're not a nerd. Well, you're here. By the way, do you know of homotopically equivalent chain complexes? I do know of them. Yeah. Do you have questions about them? Or just a shout out to homotopically equivalent chain complexes? Sometimes you just gotta vocalize some love for our chain complexes. Anyways, this paper is great. Yeah, and they give you the full construction of like how to actually build your Turing machine, how the Turing machine works. Actually, I think there's even a YouTube video where what's this guy caught a nuclear disaster video guy. I think he does it. Oh yeah. So I think in this one, yeah. So he has a video where he actually buys the deck and sort of does a computation. But like, of course, we're talking about like the way that this is set up. It's like the most basic Turing machine, right? So like, it would take you forever to just make the program like to like execute the program 1 + 1 = 2, for example. Um, but it's still fantastic. Here's another fun paper about games. I have a small little quibble. I can't remember what it is. So Mate and Omega. There's a certain way that he makes a statement in this video. Overall, great video. Absolutely, like totally recommend it. He just makes a certain claim in the video or words something that me as a picky mathematician, I'm like, well, technically it's not exactly correct, but whatever. It's an amazing video. But you should. It's worth checking out the archive paper. Oh, where is it? Actually, I think he's got it linked in the description. Oh, it's not on archive? Weird. Anyways. Oh, no way. Joel David Hampkins is an author. Huh. Go figure. By the way, I saw a tweet, or what do we call them now? I saw an X from him. I saw a tweet from him that apparently for like what is it, 14 years in a row he's been the top he's been the top poster on the top person on Mass Stack Exchange, which is wild. That's a wild, absolutely wild thing to have. Let's run Doom by setting up a Magic tournament. Hell yeah. Hell yeah. It would be amazing. It would be amazing if we could even just like... Yeah, I wonder... I haven't even thought about that because, like, yeah, you have one Turing machine with one deck, but if you have various people set up in a tournament playing cooperatively, what, like, could you do some sort of parallel processing kind of thing? Or even, I mean, you can have giant like multiplayer games. Oh, that's interesting. Just a shout out, nice. Always shout out. Feel free, yeah, everyone in chat, feel free to just give random shout outs to your favorite concepts. But confused how it related to projective injective modules. Okay, let me come back to that in a second. I just want to mention this paper. Yeah, actually, I had sent Professor Hampkins an email to be a guest to do an interview back when I was reading up a bunch on like different sizes of like inaccessible cardinals and stuff. And he did respond, and he said he'd be interested, but this was like a few months ago, and we said he's like, I'm kind of busy now, like maybe we'll aim for February. And I messaged him again in February, didn't hear back, which is how it goes. I mean, he's probably busy or whatever. Maybe I'll reach out again because I think he'd be an interesting guest. But there was already a great interview with him on Sean Carroll's podcast Mindscape. Anyways, so yeah, in here, I mean, you can watch the video to get a sense of what's going on, but basically, they imagine like an infinite chessboard, and so they set up positions like this, so they talk about like mate in 17 basically means that like one player, normally you set it up as white, one player white to mate in 17. So mate in 17 means no matter what black does, like there could be mates that happen in shorter if black plays suboptimally, but the supremum of all of the ways that it plays out, if white plays with best play, will force a mate in at most 17 moves. Oh yeah, I'm definitely a nerd. Don't get it twisted. Don't think that I'm sitting here calling all of you nerds, thinking that I'm somehow separated from that discussion. I'm the biggest nerd here, debatably. So the interesting thing though is we got mate in 17. But on an infinite board, so part of the setup here is that basically if is it white or black has some choice about where to move first. So there's something like in this picture. I don't remember what it is exactly, but it's like if depending on how far white moves the rook, white can determine how many moves it will be to be like what n for which mate in n it will be. And since that's unbounded, we call it mate in omega. Okay, it's a very loose and not technically precise description. You should watch that video and or read the paper. But actually, the paper goes on to do so much more actually than just the video discusses. So they analyze, like they're able to assign certain ordinal numbers to different chess positions, but then also they like analyze like, oh, which ordinals like can you find a position for, and then there's it's related to things to do with like computable ordinals. It's just so cool. It's so cool. I mean, I'm also a chess nerd, so I love it. But yeah, here's one. I think this is some fancy setup. This is one that's like omega squared or something. Or omega 3, omega cubed, yeah. So, good stuff. Okay, let me say a few words about projective and injective modules. Well, how should I say it? So I guess, what's a good intuitive way? I feel like this would be something that'd be good to sit down and think about for a while, how to say in the best way. But okay, so we've got, chain complexes in general. Whichever way you want to write your indexing. And, we've got these things like, I wonder if chess players can play on these infinite boards since they're good with blindfold chess. You should do a chess tournament one day. Yeah, maybe. I mean, you could definitely, I don't know. I don't know if blindfold. I don't know if having blindfold chess skills really translates to being able to play well on an infinite board. Yeah, I'm not sure that's the case. I think on an infinite board with regular pieces, I think it would be much harder to force checkmate. I think it'd be a lot harder to trap pieces. It might be nice to talk about AI and undecidability sometime from the perspective of Gödel's theorem. Yeah, I haven't really thought about how those two go together. Maybe after I say some more words about projective modules. So, Okay, how to motivate this discussion. So one thing we might want. So we know, for example, that like Hom is a functor. So we have a covariant functor and a contravariant functor, being these two Hom functors, right? From like, let's say we're going from modules to modules. And the covariant Hom is left exact. So that means that if you started with that basically means it preserves injective maps, right? So that means if you started with a short exact sequence here, and you apply the Hom functor to everything, including the maps, then you get a sequence where you still know that this map here is injective. Well, you still get a map into C, but the problem is it's no longer. Sometimes you like to sit back and think that life as an engineer is much simpler. Yeah, probably. Sometimes I think I should have just made bank as an engineer, retired early, and then done this crazy math. But here we are. So we apply the Hom functor, and then unfortunately we just can't, like over here, we can't necessarily write that 0. It's no longer surjective. So if I were to put a 0 here, I mean, I could write the 0 here, but normally we only write these zeros when it's exact. So this would not necessarily be exact anymore. But then the question is, you were going to be a painter? Well, I mean, what is math but a kind of painting? But with LaTeX is my canvas. Overleaf is my canvas. So the question is, can we put some object here to make this exact? Is there something that would go here that would make this exact? And the answer is yes. And that's exactly what X1 MA is. So basically, what X1 MA does is this measures exactly. You can still, yeah, exactly. It's right there. It's right there in your name. But what X1 does is it measures the failure of exactness. It measures, So when Hom M fails to be exact, that's the thing that measures the failure. So if X1 is large in some sense, like maybe it has large dimension, you could view that as it like really failing to be exact in a bad way. But if X1, maybe if the dimension's small or something, then you could view that as it being like, well, it doesn't fail, in a large way. It's some sort of measure of how hard how much it fails to be exact. Well, what are things which don't fail to be exact? I mean, one equivalent definition of a module being projective. It's projective if Hom P is exact. Right? So, in other words, we know that i.e. for all modules, A, Hom P A, or sorry, X1 PA is trivial, right? Because, like, again, basically by definition, a module is projective. Then this will be 0, right? So this will be this term. It will be exact here. This part will still be surjective. You've been to a low-dimensional geometry conference, and they have awesome drawings. Yeah, I would imagine. I'd imagine that's the place to go. That's the place to go for good drawings in math. Okay. So what does that have to do with chain complexes, though? Well, we want some way. Well, okay. I guess one definition you can take is like a definition of X1MA is like the module that goes here to keep this sequence exact. Well, the map that you get is also important, though. And so I guess the next part, the maybe trickier thing is to prove that the thing that goes there is the thing that lines up with chain complexes. I don't know if I can do that totally from memory. I don't know if I even want to try. But the point is how like why should projective modules have anything to do with computing X? So I forget which way we make our resolutions. I forget which one we resolve projectively and which one we resolve injectively. But okay, up to some flipping of words that I might say. I think the usual process we do is, okay, so we want to compute X to MA, right? So what we can do is we can take A, right? And basically what we want to do, so somehow the like the projective objects, right? Since those have trivial X groups, somehow those are like ripe for detecting the failure of exactness, right? Because the projective modules already are exact. And so if we try and like approximate A by exact things, right? The idea is like, so maybe A isn't exact, right? But we might, see, now this is making me start to think that we might want to take an injective resolution of A. But let me finish this again. Everything is still true up to some flipping of things. Actually, no, I don't want to tell you lies. I should probably look it up. So, which way do I put it? Projective resolution of M. Okay. Yeah, so let's do it that way, yeah. I knew because A's in the second component. So okay, so let's yeah. And this makes more sense. Because right, so we've looked at this exact sequence, right? If M was exact, if M was projective rather, because it's in the first coordinate, that would make this term trivial, that would make this thing exact, right? And so, okay, a priori, we don't know if our random module M is exact or not. So what we can do is try and we can come up with an approximation of M by projective objects, right? Would I recommend joining grad school for master's, which is more famous but extremely fast-paced, or grad school less famous but equally ranked, which is slower paced, so you feel your basics are lacking? I say go with the more famous place, honestly. Yeah, because I think you'll like Yeah, the more famous place, I mean, that just looks good. It just looks good, and people can pretend that everything's all meritocratic or whatever, but yeah, the at the end of the day, the name of the place that you go to, it does matter. And here's the thing. So definitely there are people who are just like super geniuses, and they're really just like inherently good, and then on top of that they work hard. But I also think that like when you go to a better place, it makes you better. Like at this more famous place, there's probably more famous mathematicians who are working on cutting edge stuff, and so if you go there, there's a better chance that they'll be able to like pull you in and give you some insight. Like my feeling is that a lot of these people like who go to Harvard or Stanford or something is like you like they're going there, and the thing is they're having like they have classes on like these complicated fancy on these fancy complicated things like the cutting edge technology, like whereas a lesser known university, they're just teaching normal classes about, oh, here's like basic like algebraic topology as we did it 100 years ago and stuff, and like most universities are doing that, whereas meanwhile the other like bigger, more famous universities, like those are the ones that have like actual courses about like stacks and adic spaces and whatever, and so I think part of what makes the people who go there better is that they just have access to more of those actual classes. So go there. You're still not sure if you'll get a PhD or exit for quant finance. Yeah. I don't know. I kind of say go to quant finance. Go to quant finance. Retire at like, I don't know how old you are, but like, yeah, make stupid money, retire at like 35, and then go like read textbooks on a beach for the rest of your life. First day of grad school was soul crushing, but we were an adapting species. Yeah, exactly. Like you'll just adapt and grow. Good. Well, good luck. Yeah, I do wish you good luck. You'll be fine. If you follow this channel, you'll be fine in grad school. uh, yeah. Yeah, so okay, so if M if M is projective, I mean we're done. Your mind says it's true, but at your heart you feel like a fraud. Well, then, one post I liked about the imposter syndrome was just to lean into it. It was just like, it just said, it was like, oh yeah, just lean into the fact that you have everyone fooled and view it as you being like, ha ha ha, I've tricked them all. And I really like that antidote. You're 21 this year in June. Well, fantastic then. Yeah. So yeah, honestly, go into quant finance and retire by the time you're my age. And then do all the math you want. You could make so much money that you could just pay a Harvard professor to sit down with you and teach you whatever fancy math after that. That would honestly be my advice. And you'd even have time for a Fields Medal after. Yeah. So M may be projective, maybe not. I mean, if we want to approximate it by projective objects, if it already is projective, then we're done. But we don't necessarily know. But it is true that we can, be exactly like Jim Simons. But But it is true that we can find a projective thing that quotients onto it. And we would maybe like that to be an exact sequence, and we say, okay, well, maybe, if this was an exact sequence, that's saying that M is isomorphic to a projective thing. But so maybe that's not possible, but we could also cook it up so that maybe we can cook it up so that there's at least two projective objects in a row that we can approximate M by. Okay, that's also not always possible. So you might say, okay, we might have to take another one. But what we can always guarantee is that we can find some, potentially infinite sequence of projective objects that approximate M. You left the hope for fields at age 14 because I have no IMO background, and IMO has a strong correlation. Yeah, but I mean, just because, yeah, I mean, you can win the Fields Medal without an IMO. But yeah, like most likely, like people who are doing Fields Medal worthy research were like super genius. You know, it's like if you weren't playing chess, you know, if you weren't like a 2000 rated player if you didn't start playing chess by the time you were 3 and you weren't 2000 by like the time you were 10, then like you're not going to be world champion ever. That's just true. Same thing with like Fields Medal. Like, yeah, if you weren't doing university level mathematics by the time you were like 13 or something, I'm sure there are Fields Medal that used to be like that, but I just like Thurston and want to study that. Yeah, I mean, yeah, just it doesn't make sense to like, try and be motivated, like, I'm gonna get a Fields Medal. That's not gonna carry you through. That's not gonna carry you through like grad school and stuff. That's not. You need to actually enjoy it. So we've approximated M by these projective objects, and then what we can do is we can apply X, or we can apply HOM into A, right? And then what we're going to get is HOM MA HOM P naught A. Actually, I think we can cut this first term off because HOM P naught A ends up being isomorphic to that, I think. But then the sequence keeps going, right? Because we've taken a contravariant, we've applied a contravariant functor. And then, so hopefully this at least thematically makes some sense that like the reason why projective modules have anything to do with these like chain complexes is that we take, it's like we don't know how much M fails to be exact. We approximate it by this chain of objects which are exact. And so since we also make this an exact sequence, right? So this sequence here has no cohomology or homology, whatever, right? But it's exact at each of these terms. And so the thing is, it's perfect because this thing, it currently doesn't have any homology, but then we apply a functor to it. And so therefore it might it will pick up cohomology. And so because we're starting at a baseline of 0 in some sense, when we apply this, it will detect some sort of like failure of exactness. And that is why we define X I of MA. I mean, this is only a definition up to isomorphism, but we define it to be the ith cohomology of this complex. But then, okay, now we need to do some work and prove the theorem that, that X1 that we get there, like, really is the thing that goes here. So, Fields medal is overrated. Well, I don't know. I mean, don't get me wrong. I'd love to be a Fields medalist. I don't think it's going to happen. I'm not even trying. But, yeah. The whole prizes thing in academic disciplines is nonsense. It makes sense if it was competition. But this is funding done to improve the world or give tools to improve the world. Yeah, I mean, I don't know. I do have complicated feelings about awards and stuff. Like, I do think it's worth... I do think there is value in recognizing the work of others. I just want to see, how's this pen write? Oh, that looks nice. Maybe I should write with this more. Kind of like the pen. Or maybe it's too messy, because I'm too messy. Anyways. Yeah, it is nice to be recognized for your accomplishments. And so I do think there's value in that, in a certain sense. On the other hand, yeah, when it comes to things like the Fields Medal, it's like, what's the point? It's like, okay, it comes with a lump sum of money, but like, by the time anyone's like, if you're winning the Fields Medal, you're already at a top institution. You're already a professor at a top institution. You're already being paid pretty well, so it's not like what does that money mean to you? I mean, it's still nice. Like, don't get me wrong, I'm not gonna turn down the money, but like, it's like, it doesn't really mean that much. You know what I mean? Because it's not like if you're winning a Fields Medal, it's not like you're probably not overburdened by teaching duties, and it's like, oh, that money would be so nice so that I could afford to skip teaching duties. You know what I mean? Like you're probably already at that position where you can just do what you want. And then also when you win the Fields Medal, I mean, I don't know. I'd have to ask people who win the Fields Medal. Like, I think there are some people who are very pretentious and sensitive about their accomplishments, but also like, I would imagine that by the time you've done the Fields Medal, like, you've already gotten all the accolades, right? Like, you already know how good you are. Your colleagues already know how good you are, and that's already been expressed, right? You've already made those accomplishments. You've already proved those theorems. You've already been invited to be like keynote speakers at conferences on your groundbreaking research. So, yeah, I don't know. But I get, I'd have to talk to more Fields medalists to see how they feel about it. But, my guess is that it probably, like, yeah, on one hand, it's nice to reach that thing. On the other hand, I could imagine that as a Fields medalist, well, maybe it doesn't mean so much, because it's like, yeah, I already did the amazing work, and I'm still going to keep doing the amazing work. I don't know. Do I think there should be another Fields medal for under 30 mathematicians then? Nah, I don't know. I mean, maybe my opinion would be different if I was anywhere near the caliber of mathematician that would ever be in the running for such a thing. Maybe I have a very different opinion. Probably I would be, but yeah. Should there be one? I don't know. I mean, yeah, I get, like, I'm not gonna say that there shouldn't. But I'm also not going to take the stance that there should be, for the exact same reasons. Like I feel like over 30, under 30, whatever, like, whatever your motivation is, like, I just don't think that many people are doing it for the award. Don't get me wrong. I'm sure some people are very invested in the prestige they might have built around themselves, being award-winning mathematicians, but even those people who are maybe not, like, the most humble, even though, and to be clear, I'm not saying that everyone or even a majority of high-level mathematicians are like that. Certainly doesn't seem to be the case for most of the big names that I've met. But even though they might there might be some ego developed around these things, that's still not what fundamentally drives these people to do this work. You don't. It's not. It's not glory that drives any of these mathematicians. Not when it comes to that level of work. It has to be an inherent love of the game. Almost 30 under 30s is almost impossible. Like who you got, Sarah Deline. Yeah, and I mean. Needs to be medals exclusively for people over 40. Well, there is the Abel Prize, right? That's like a lifetime achievement award. In fact, when you finish, you'll go back to your country and teach kids to do math research, ideally. Yeah, it sounds nice. Yeah. If you've done anything notable under 40, you're disqualified. Yeah, if you've done anything. Yeah, I don't know. I don't think there'd be a lot of winners of that award, to be honest. But, yeah. Anyways, my coffee's done. You know the drill. Time to hit the gym, and then hit the books. As the same should be for all of you. Gotta get some oxygen in that brain, and then improve some theorems. So, I'll probably see most of you tomorrow. Yeah.